I love the Fibonacci numbers. I find them so interesting, but the internet is kind of ruining them for me. At their core, the Fibonacci numbers are the sequence that starts with 0, 1, 1, 2, 3, 5, 8, and you add each of the two previous numbers to get the next one. I love that this simple mathematical idea is able to describe lots of natural phenomena, such as the spacing of seeds on a sunflower, and the number of spirals left and right on that same sunflower is often a Fibonacci number. For people who have heard of the Fibonacci sequence, they often believe two things about them. One is that they have some kind of connection to human aesthetics, and two is that they're named after the person who discovered them. But both of these facts are wrong. When you type the word Fibonacci into a search engine, you can come face to face with some of the worst pseudoscience slop you'll ever find. Here are some examples. This one I don't think has a single correct fact in it, but it is playing off the sense that people find the word Fibonacci to be mysterious. And this one here is claiming that your life will be forever changed if only you learn about Fibonacci. And maybe that's true if it inspires within you a lifelong love of learning mathematics, but I don't think that's what they're referring to. This one is claiming that the Fibonacci sequence is literally everywhere, and that's not true either. It's in a lot less places than people claim. It does feature most prominently in the world of phyllotaxis, which is the arrangement of parts of a plant, and other things that have the same sort of structural optimization. But most of the examples here do not fall under that category. And it doesn't prove that the entire universe is interconnected. I called this Fibonacci slop, and I'm using the word slop here to refer not just to things that are AI generated, although a lot of this is exactly that, but also to ideas that are rebaked over and over again and lose a little bit of truth every time. So what is it about this simple list of numbers that has such a power over our imagination, and where does the truth lie? Well, I think it starts with going back to Fibonacci himself. I have here Fibonacci's Liber Abaci, which is his original manuscript from 1202, where he first describes the Fibonacci numbers. It is this book that is the reason the Fibonacci numbers are named after him, even though his real name wasn't Fibonacci, it was Leonardo of Pisa. For all the fame that the Fibonacci numbers have, I've never actually seen someone going through this book before, and I was curious to know what Fibonacci himself actually said about these numbers. Did he ever make any of these wild claims? Did he ever say that this sequence was some kind of connection to nature or God or anything else? What was Fibonacci actually doing that led to him discovering these numbers? As I was researching this book, I found that it was a very influential textbook and had a huge impact on the history of mathematics. In a way, you can thank this book for the fact that math class today looks the way it does. Firstly, he introduces the Hindu-Arabic number system to the Western world. This wasn't the first book introducing them, but it was the first one aimed at workers and tradespeople. The other books had been aimed solely at academics. This was teaching a general public this concept of 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0, and he was teaching it to people who had previously been using Roman numerals. The book title is Latin for Book of Calculation, and its second major influence on modern math class becomes obvious once you start to read it. It's really hundreds of word problems used as examples to teach math concepts. To drill down this new idea of the number and place value system, Fibonacci comes up with every conceivable example that might be relevant to the merchants and traders who might be reading this book. Some of them are bordering on a little absurd, and so it feels like the original source of problems that are like, Jimmy bought 45 watermelons from the store. How much change does he get? He's made everything very real world and is teaching theoretical ideas through these somewhat relatable example problems. So let's take a quick browse through the book. In the prologue, Fibonacci talks about how, as a teenager, he left Italy to join his father in Algeria in North Africa because his father was working there as a merchant and customs official. There he encountered the Hindu-Arabic numeral system, calling it the 9 Indian figures, which was taught to him through Arab scholars and merchants. Chapter 1 starts with explaining how you can put these digits together to form numbers using the place value system. This is all new. The people who would be reading this book would be using Roman numerals up until this point. And it's not just a new way of representing numbers that Fibonacci is introducing here. By using this system that we are all familiar with today, you actually unlock, I guess, the powers of arithmetic, of being able to add, subtract, and multiply numbers in a more visual way that you can keep track of on paper. Previous to this, the traders would be using one of two methods to carry out their calculations. The first is finger arithmetic, so they would actually hold the values on their fingers using the method described actually in one of the first pages of the book, or they would use a mechanical abacus. So we see a bit of a conversion example here from Roman numerals to the new system. Once you've got a grip on how these numbers work, he shows how to multiply them, basically gives some multiplication tables, the kind that, we would still memorize in school today, and the same for division and addition and subtraction. Fibonacci is explaining step by step what digits to write where and what to do with them. A modern-day textbook would probably just give a general formula and maybe an example or two, and then you can simply plug numbers into that formula. But that kind of algebraic notation was still several centuries away. Instead, Fibonacci relies on giving as many concrete examples as possible, each using slightly different numbers. It's more like a mathematical cookbook. You'll notice that fractional numbers are written kind of strangely. He's written the fraction part before the whole number, and these numbers would be built up from right to left. Each new fraction to the left represents that part of what is to the right. Might sound a bit confusing, but it's like if we were to write the decimal 1.729 out like this, where the 1 is on the right, then 7/10, then 2/10 of a tenth, or 2/100, then 9/10 of a tenth of a tenth, or 9,000. Here's an example problem about buying 100 hides. If 100 hides are worth this amount of pounds, then how much are 32 hides worth? Here's another example of buying large quantities of things. We're buying now 100 canes of cloth, or a ton of peas and cheese. Looking through here actually gives you a nice sense of what medieval life was like, or at least the items that they had and wanted to trade. There's pepper or silver and goat skins. And then we get into trades, like trading pepper for cinnamon, or even for saffron. I'm sure we still have problems like this today in math class, and also a tricky problem on a man who buys 30 birds of 3 kinds for 30 denarii. The real juice of this book starts at chapter 12. There are some quite interesting and also funny problems in this chapter. On finding the life of a young man, or on the lion who was in a pit, on 2 ants, one of which follows the other, on 2 ships that meet, and then we have this seemingly absurd question, on a butt that has 4 holes, one above the other. I was very confused at first, but it does seem that a butt is something that stores barrels, because on the next page they're talking about emptying barrels, and Googling it, it looks like it was a medieval unit for a measure of wine. And so a buttload of wine is about 475 litres. There's a lot of figuring out how to share things between people, including this problem about sharing denarii between 4 men, which is apparently an unsolvable problem. And I just really love some of these titles. The man who hastened to Constantinople to sell 3 pearls. There are a lot of questions about what to do if you and your whole squad find a purse together. We've got a purse found by 3 men, a purse found by 4 men, a purse found by 5 men. In fact, the finding of a purse by multiple people is described in such excruciating detail with so many examples that one is led to believe this is some kind of common occurrence, or it's just symbolic on how to share things in general. This one is truly incomprehensible. On him who went into the pleasure garden to collect apples. You can pause this one if you want to try and figure it out. This one sounds like some kind of comedy routine on two men with fish and the customs agent. There was no English translation of this book for 800 years, which is kind of crazy given how influential it was. The reason might just be that there wasn't a lot of demand to read it, even from mathematicians. Because apart from some of these headings, the actual meat of this book is really hard to read and kind of boring because we already know how to do, calculations with numbers, and we can teach people how to do these things now with less confusing ways. It shows that math is really cultural, even if we don't think it is, because our upbringing and our education makes this book hard for us to read, even though it's the same familiar stuff that we would learn in school. What I've been showing you here is the English translation by Lawrence Sigler. And at the start, we actually see that he passed away before this book was published. There is a really interesting story even behind that. Lawrence knew that a translation of this book should exist, so he taught himself Latin to do it, using only a small copy of a compact Latin dictionary. He started with another of Fibonacci's books called the Quadratorum, and then moved on to this Liber Abaci. However, he was diagnosed with cancer while working on it and had to race to finish. He completed his translation in 1995, but his publisher knew nothing about his ill health and kind of just stalled on the book and didn't publish it. They were waiting to have more resources or to be in a better position to publish it. Unfortunately, it was still just sitting with them when Lawrence Sigler died. The hero of the story really then became Lawrence's wife, Judith Sigler. She kind of took over the project. And because the publisher didn't know that Lawrence had even been sick, Judith actually didn't tell them. She pretended to be Lawrence, replying to emails from the publisher and asking them when they're going to publish it. She was worried that if they knew he had died, the project might be scrapped. There was another challenge. The book needed to be typeset, and the mathematical formulas and columns and tables needed to be put into LaTeX, which if you're a math or science student, you'd be familiar with. It's like learning a whole nother language again just to type up your document. Judith then had to teach herself LaTeX and is the one who formatted all of these tables throughout the book. She became essentially another layer of translation in this story, yet another translator of Liber Abaci. Eventually they published with Springer, who weren't the same publisher that held up the project in the first place. And in 2002, 800 years after Fibonacci wrote it, this English translation was finally published. Right, so we've been through all this, and yet there's no sign of the so-called Fibonacci numbers. No golden ratio or spiritual claims. In fact, everything has been very rooted in the practical. So let's go to page 404. It's in chapter 12. And this is where we will find the mention of the numbers that will go on to be called the Fibonacci numbers. It's titled, How Many Pairs of Rabbits Are Created by One Pair in 1 Year? It's a population puzzle. You start with one pair of rabbits, one male and one female. The rabbits take 1 month to mature. Once mature, each pair produces a new pair every month, which are again one male and one female. And none of the rabbits ever die. So in the first month, there's just the original pair. In the second month, that pair matures, but there's still only one pair. In the third month, the mature pair produces a new pair. So now there are 2. In the fourth month, the original pair produces again, and the younger pair matures, giving 3 pairs. In the 5th month, the 2 mature pairs each produce a new pair, bringing the total to 5, then 8, then 13, and so on. We have 377 by the end of the year. Each month's total is simply the number of pairs from the previous month plus the number from the month before that. And Fibonacci doesn't say much more about it after that. It's just one practical example that relates to rabbit population growth. It was included because it's an easy problem for practicing how to use this new number system. Turns out its author's greatest fame would rest on this one little problem. So I mentioned at the start that one of the myths that people believe about the Fibonacci numbers is that they are named after their discoverer. They are named the Fibonacci numbers because of the book we just looked at, but Fibonacci, or Leonardo of Pisa, did not actually discover them. He was merely the first to popularize them for a Western audience. In Fibonacci's book, he was bringing back maths he had learned from the Arab world and indirectly from Indian mathematicians who had been there. So if anyone discovered the Fibonacci numbers, it was the Indians. One of their earliest appearances was actually in a Sanskrit text on poetic meter. This is attributed to Pingala, somewhere around 400 BCE. This wasn't about rabbits or spirals, instead it was about poetry. The Indian scholars analysed long and short syllables in the poetry and asked how many different possible rhythmic patterns there were in a given length of text, so it was really a combinatorics problem. In Sanskrit poetry, there are these units kind of like syllables, and they're called mora. You can have one that's light, and it's denoted by this vertical line, and that takes up 1 unit. Or you can have a heavy syllable that's denoted by this S, and it takes up essentially 2 units. Then, if you ask how many different ways there are to assemble a certain line of poetry which has a set length or a set mora, then these are the options that you get. There's only one way to have 1 syllable, and that's with that light one. But there's 2 ways to have 2 morae, which are the heavy syllable or 2 of the light ones. There's 3 ways to have 3 morae. There's 1, 2, 3, 4, 5 ways to have 4. There's 8 ways to have 5. And the next table lists the 13 ways that you can have a poem of 6 morae. 1, 2, 3, 5, 8, and 13 are all Fibonacci numbers, and the pattern continues as this poem grows longer and longer. The name Fibonacci sequence didn't actually come until much later. It wasn't until the 1870s that mathematician Edward Lucas used the Fibonacci nickname to refer back to the numbers from the rabbit problem. But ever since then, the branding has stuck. So sure, Fibonacci didn't actually discover these numbers for the first time, but despite that, he actually was one of the most influential people in the history of mathematics. He had the ability to take what was at the time very novel and difficult mathematical ideas and make them accessible to a wide range of people. There's a book called Finding Fibonacci, in which the author, Keith Devlin, describes Fibonacci as almost a bit like a Steve Jobs character. Steve Jobs didn't invent the computer, but he did recognize that the computing technology that other people thought was perhaps too niche or specialized should actually be brought before a wide audience, and that we should teach people how to use it. Fibonacci also reminds me a bit of the Ada Lovelace situation, where the role of translation and communication was actually really impactful to the legacy of the science. Liber Abaci was a major trigger for a revolution in arithmetic and finance that occurred in Italy not long after this book was published and then spread throughout Europe. Right after the book was published, we also saw the rise of something called abacus schools, which were these medieval schools where merchants would send their sons to be educated. Students in these schools for the next few hundred years would work through these smaller, more compact little textbooks that did have their roots in Fibonacci's work, and it spawned this sort of genre of medieval math or school-related books. One of them was called the Treviso, and I'm going to go through that and look at some medieval homework in my next video. There's no evidence that Fibonacci was reading Sanskrit text directly, but through his Arabic teachers, he was exposed to some of these ancient Indian mathematical ideas, and through him they traveled west. What changed in these mathematical problems was the setting. Whilst a lot of the Arabic examples were focused on how to divide up things like land or inheritance between family members, Fibonacci took those same ideas and applied them to trade and business ventures. And that's what makes Fibonacci's legacy so strange, because his manuscript did change the world. Yet today he is way more known and remembered for this short, simple problem about rabbits. So why is that? A lot of the fascination with the Fibonacci numbers comes from how often they do turn up when you go outside and count things. If you count the number of petals on a flower, you might often end up with 3, 5, 8, or 13. It's not every flower, but it's enough to feel like more than a coincidence. If you look at a pine cone or a pineapple, you'll see that there are spirals running in 2 directions. If you trace how many of those spirals there are, you'll often end up with pairs of numbers like 13 and 21 or 34 and 55. These are Fibonacci numbers. The key mathematical fact underpinning why the Fibonacci numbers seem to occur like this is actually their connection to an equally famous mathematical constant known as the golden ratio. As you move further along the Fibonacci sequence, the ratio between successive numbers approaches a constant value. That number is called phi, or the golden ratio, and just like pi, it is also irrational, meaning that its decimal expansion goes on forever. It begins with 1.61803, but keeps going and never fits into a repeating pattern. When you use this number to space points around a circle, something interesting happens. Each new point falls into the largest available gap. There's no simple repetition. If you divide a full 360-degree turn according to the golden ratio, you get an angle of 137.5 degrees. Repeatedly adding that angle distributes points remarkably evenly around a circle. For a growing plant placing new leaves or seeds, that's a very efficient way to avoid overlap. But petals, leaves, and spiral counts have to be whole numbers. So what shows up in the visible structure are the nearest whole number approximations to that ideal ratio. And those approximations tend to be consecutive Fibonacci numbers. That's why the sequence keeps appearing in sunflowers and stems. Fibonacci didn't discover the golden ratio. It first appears in Euclid's Elements in a geometric problem about dividing a line. Euclid calls it the extreme and mean ratio. Things get kind of crazy in the 15th century when an Italian mathematician, Luca Pacioli, gave it the evocative name divine proportion in his book. This book was illustrated by Leonardo da Vinci, which intertwined da Vinci into the story of the golden ratio, and meant people would forever claim that da Vinci's own artworks used this ratio, even though he was kind of just illustrating this book for a friend. It was first called the golden ratio in an 1835 book written by the mathematician Martin Ohm, whose brother is the one who discovered Ohm's law. As Keith Devlin says in his book Finding Fibonacci, with the acquisition of not one but 2 suggestive names, one hinting at God, the other at wealth, it is perhaps not too surprising that various false beliefs and superstitions about the number soon appeared and began to flourish. One pretty persistent myth says that the ancient Greeks thought that the golden ratio made for the most aesthetically pleasing rectangle, and so they built it into some of their structures, including the Parthenon. But if you look at careful measurements, they don't actually support this claim, and depending on which parts of the building you choose to measure, the ratio differs. Claims like this are also false on purely mathematical grounds, because if you really think about it, the golden ratio is an irrational number, meaning that it really can't be described as any ratio of 2 rational numbers. That means no physical measurement can ever confirm it exactly. At best, you can only get approximations. That makes claims about exact golden ratios in ancient buildings especially difficult to justify. Take a look at all these rectangles in the paper titled Misconceptions About the Golden Ratio by George Markowski. Can you spot the one with the golden aspect ratio? Which one's length is 1.61803 ... times its width? Or just pick which one you find to be the most pleasing rectangle. The author of this paper showed these rectangles to a lot of people and asked them which one they found to be the most pleasing rectangle. The most common answer was actually this one, but that one doesn't most closely approximate the golden ratio. It's actually this one here that does. Or if you want to talk about 1 over the golden ratio, it's this one here. Humans might just like rectangles roughly this ratio, maybe even between 1.5 and 1.9, but there's no evidence they actually prefer the golden ratio, which is very specific. Another common claim says that if you divide your height by the distance from your belly button to the floor, you'll get the golden ratio. Apart from the fact that bodies vary widely, there's nothing special about landing near 1.6. If you start dividing different body measurements by each other, you can generate all sorts of ratios that look suggestive. You could generate almost any ratio you like, depending on what you choose. There are lots of academic articles and books that analyze claims about the Fibonacci numbers and find a lot of these to just be myths. And yet these myths persist, and that's because we enjoy believing in them. We do want to believe that the world is mathematically destined. Fibonacci had just wanted to educate the world about numbers, not to have his legacy become something associated with myths. It's also important to note that neither Fibonacci nor the ancient Indian mathematicians such as Pingala ever made a connection between their work and the golden ratio. This link between the Fibonacci sequence and the golden ratio wasn't spotted until much later by mathematicians who were looking into the sequence more deeply. Where the golden ratio does seem to hold up under scrutiny is in plant growth. In placing petals, seeds, and leaves, the efficient spacing matters. Growth patterns that minimize overlap and maximize exposure tend to survive. It avoids lining things up in repeating patterns. When you round that ideal arrangement to visible whole numbers, the Fibonacci numbers naturally emerge. That's why you see them in a sunflower, but it does not explain the stock markets. And yet, if you search Fibonacci online, you'll find endless trading strategies built around using Fibonacci numbers, mostly because the name sounds mathematical, but without a solid mechanism grounded in economic theory, they probably don't mean anything at all. I care a lot about the Fibonacci numbers because I feel like, in a way, they were my gateway drug into mathematics. I distinctly remember them being the first mathematical idea that I found interesting, and I didn't learn about them in class or at school, but rather independently while doing some of my own Google searching. And I think that helped them become the very first mathematical puzzle that I had to chew on and think about. As I would walk in nature, I would be constantly looking out for plants whose arrangement of leaves seemed to abide by this pattern. I feel lucky that the page that I first read about the Fibonacci numbers on had some mathematical context, because if that hadn't been the case, then my first learning about it would have perhaps been from a less grounded angle. Instead of it being my gateway into mathematical puzzles, it could have been my gateway into conspiracies. So I do feel lucky for the context I found them in, but that's not something that we really control, the context of discovering information. But it does make a big difference to how we choose to hold on to ideas and what we do with them. Quantum mechanics is also a bit like this. It matters a lot where you hear about it for the first time, because quantum mechanics has a lot of inherently interesting ideas, paradoxes, and mysteries. So you better hope that you first encounter it in a physics class where you have a teacher who can help you place it within the context of modern physics. If you encounter words like quantum first from someone who is trying to sell scam energy healing products, then you'll still find these ideas inherently captivating, but you'll have a different mental anchor of what they're relevant to. I believe people do have a deep fascination with numbers, especially when they're presented in an interesting way. And sometimes that interest drifts into numerology, the belief that numbers secretly govern our destiny. And mathematics absolutely does describe aspects of the world, and we use equations to describe so much of what's going on around us, but describing patterns is not the same as imposing significance. Once you strip away the mysticism, the mathematics of the Fibonacci numbers actually get more interesting, not less. For example, there is a group called the Fibonacci Society that has been together since 1963, and they publish a journal called the Fibonacci Quarterly. It's devoted entirely to studying the Fibonacci numbers and related sequences. They're studied not as spiritual symbols, but just as interesting maths. A lot of what appears in that journal falls under something known as recreational mathematics, recognizing that there is fun and also a kind of magic to solving puzzles. And the Fibonacci sequence does turn out to have an incredible number of real and surprising properties. For example, Fibonacci numbers show up in combinatorics, the number of ways to tile a 1 by n strip using squares and dominoes follows the Fibonacci sequence. They appear in graph theory in structures called Fibonacci cubes, and in computer science, where Fibonacci heaps use properties of the sequence to optimize algorithms. There's Fibonacci coding in data compression based on the fact that every positive integer can be written uniquely as a sum of non-consecutive Fibonacci numbers. There are deep connections to many fields because these numbers appear whenever a structure grows step by step, and each new step can be formed from two previous states. None of that is mystical, it's just the structure of counting. And that's what I think Fibonacci would have appreciated the most. Not the Instagram posts about divine proportions or the products for sale covered in golden lines, but the fact that more than 8 centuries later, people are still discovering new applications, new theorems, and new surprises hidden within this sequence of numbers once used in his rabbit problem. The story of these numbers really reminds me that so much of our world is about communication and packaging. Starting way back at the ancient Indians, every time these ideas were translated or repackaged or shared or communicated, they changed history a little bit. And I'm talking about even those translations along the way to bring a book that I could show you in a YouTube video. And we're all having an impact on the future from now based on what we are communicating and what we are sharing and translating as well. The legacy of the Fibonacci sequence is really still on a knife edge between being grounded in reality and inspiring people to learn more about it, or falling into the abyss of pseudoscience and being used as proof of all sorts of random things. If you know of any cool applications, please share them in the comments below. I think the role of science communicators in this story is a really important one, and hopefully we can show people some really cool math that inspires them. So the next time you hear Fibonacci's name being used out in the wild, do question the context. When you apply critical thinking to Fibonacci, you often find that the truth is more fun and exciting than the fake stuff. Thanks for watching this video, and thanks to my Patreon supporters for making it possible. Pictured here reading my book is today's Cat of the Day, Mink, submitted by my video editor, Noor. I am looking for some more Patreon cats to feature on this end screen, so if you'd like to submit your cat for 15 seconds of fame, please consider supporting my channel over on Patreon. And if you're already a patron, please email me through a picture of your cat. Non-feline cats are also accepted.